We are introduced to some properties of matrix addition. So if A, B, and C are m by n matrices and A and B are scalars, then the following 6 properties hold. First of all, A plus B is equal to B plus A. So matrix addition is commutative. You can rearrange the sums in any which way. And if you're talking about adding 3 matrices together, you could add the last 2 matrices first, and then whatever you get, add A after. Or you could add the first 2 matrices first, and then whatever you have from that, you can add C after. So sometimes you have various matrices involved in a computation, so it might be more convenient to add some matrices first than others because the numbers are easier to work with. So this tells you that that is perfectly fine to do. The property 3 and 4 are kind of obvious. For property 3, it says that when you take a matrix and add the 0 matrix, you get the original matrix you started off with. For example, 1, 2, 3, 4 plus 0, 0, 0, 0. What would that give you? Well, the matrix 1, 2, 3, 4, right? This property seems very obvious, but there's a reason why we take time to mention it. I'll talk about that shortly. In the same way, property 4 seems obvious. That if you have a matrix, let's say 1, 2, 3, 4, what can you add to that to get back to the matrix 1, 2, 3, 4? Well, that's going to be the matrix consisting of all zeros, right? Again, seems fairly obvious, but there's a fundamental reason why you would care to say this. Before we talk about that reason, property 5 and 6 tells you that when you're talking about matrix addition and scalar multiplication is distributive, so you can take those scalars and distribute them right into each individual matrix. And also, matrices are distributive, so you can distribute that matrix right through into those scalars. These are properties that we take for granted because we're so used to using them in algebraic problems. Consider 3x plus 5 equals 7. How would you solve that equation? Well, one way to do it is to ask yourself, is there something you can add to 5 to give you 0? So you could say you're going to take both sides of this equation and add negative 5 to it because you have this property of real numbers that 5 plus negative 5, those guys are additive inverses of each other, and you would get 0. And then 7 minus 5, that's a 2. And then would you say to yourself, hey, 3x plus 0, is it going to be 3x because 0 is the additive inverse under addition? You probably wouldn't say that, right? You would just say, well, anything plus 0 is going to be that same thing, right? And then you can multiply both sides by 1/3 or divide both sides by 3 to get x equals 2/3. If you were presented with this problem, you wouldn't really go through these steps, but these steps are in the background, making sure that your algebraic system is functioning properly, so that it's airtight, so that there is no debate of what your answer is. These tools make sure that the algebra works, and these properties are saying that matrices have those same tools. So we can take this idea and solve equations like the following. Let me put a matrix A there. In the same way that you solve the problem above with real numbers, you can apply those properties for this equation below with matrices. To get things started, you can consider how you would get rid of that guy. Well, there's a matrix that you can add to both sides to get rid of that element, right? The matrix -1, -2, -5, 4. But instead of taking time and actually writing out those details on both sides, I'm just going to take this matrix and subtract that matrix, and whatever I get, I'll write down on the right-hand side. So 3a is equal to 2 minus 1, -5 minus 2, 4 minus 5, 7 minus 4. And then I can multiply both sides by 1/3, and a would be equal to 1/3 times 1, -7, -1, 3. And if I distribute the 1/3, that's 1/3 minus 7/3 minus 1/3, +1. Done. So again, those properties are making sure that this algebra is airtight and that this has a valid solution.